Okay, thank you, Tom. Well, I asked him to introduce me as an awesome guy. Well, I want to first thank the organizers and for the hard work and for having me here to share what we have been doing for the last few years. And good morning, everyone. And my name is Po-Lun Ma. This work is done by several members. I'm working on our projects, and that's Andrew Geis, our chief AI scientist, and Matt Christensen, Meng Huang, and Yang Shi. Both of them are were my postdocs, and now they're scientists. And then Hugh Morrison from NSF NCAR, Vince Lawson, and Mike Preacher. And we started working with Mike when he was still a professor at UC Irvine, and then he moved on to NVIDIA. So we continue to collaborate. So this is great. So this is a figure produced by ChatGPT because I was trying to draw how the different components in the atmosphere model should look like, and then couldn't really make it look pretty enough. And so I decided to let ChatGPT give it a try. And it does a pretty good job. So we know that the atmosphere model consists of a dynamical core and several physical parameterizations that includes the radiation, the cloud microphysics, convection turbulence, cloud macrophysics or the cloud fraction parameterization, gravity waves, aerosol chemistry, land surface fluxes, and so on and so forth. And we have a bunch of prognostic variables to predict, and then that's how we simulate the Earth system. I was talking with a few colleagues at PNNL in the past several months, and I also shared this sentiment with a few colleagues here the past few days, is that after being involved in the model development for several cycles now, we feel like for every proposal we wrote and for so many papers that we wrote, we have this very common statement in papers and proposals that due to computational constraints, our system model has this coarse resolution problem and oversimplified parameterizations, and that limits the Earth system predictability. And so in this cycle, we're going to propose to do X, Y, Z that will address either the coarse resolution problem or the parameterization problem, right? But then after the development phase is done and we put together the new parameterization into the model, and we were so hopeful that the simulations would just magically be much better, but it never does that way. And it sometimes even perform better in the metrics that we design for these parameterizations to perform better. So what's wrong here? And so for me, my area is about the aerosol and aerosol cloud interactions. And this is a topic that you can see from also many papers that people like to start their paper or sentence by saying aerosol and aerosol cloud interactions is one of the major uncertainty sources in Earth system prediction. I can just read that out loud, and it's just the same thing over and over again. And you can see the estimates. The uncertainty range is still so large after decades of research. And for the DOE Earth system model, it's particularly a problem because as you can see here, the version 1 and version 2 model have the aerosol effective radiative forcing about minus 1.5 watts per square meter. And that is within the range of the expert judgments, the multiple lines of evidence, and also the multi-model intercomparison estimates. However, the model appears to be very sensitive to these aerosol effects. And you can see these large drops in this temperature in the historical time period. And that's a concerning thing because that's one of the important metrics that modelers would like to use. So this doesn't look good. So we're trying to understand why is that and what are the general biases. So I'm pointing out some common biases in many Earth system models. So one of them, the first one I would say is the low droplet number concentration. And that is very important here. So this is a study that we done, this published last year. This is done by a graduate student at UW, and she moved on and became a postdoc there, working with Raj Mashan and Rob Wood and others. And we collect the observational data from droplet number concentration, and this is the E3SM result. You can see this is a factor of 2 underestimation for the droplet number concentration in Southern Ocean. And the CCN is also lower in both boundary layer and free troposphere. Aerosol number larger than 70 nanometers and larger than 11 nanometers are also showing the same issue here. So we have low background aerosol number and low droplet number, and that makes the clouds are more susceptible to any aerosol perturbations, because in a clean environment, your increasing aerosol number will make the cloud much more brighter than if you are in a situation where the cloud already has a lot of droplet number, so the aerosol effects will be saturated. And another problem here is that we, in the past several years, we've done a lot of research trying to understand the aerosol cloud interactions, comparing the models and the observations, and try to develop those process-oriented diagnostics. And these are all these things that we published in the past few years. So on the top panel, you can see the joint histogram of ND and CCN. And on the left is the satellite observation. On the right is the E3SM version 2 model. I think 2 things I want to point out. One is that you can see the model's slope is much more sharper, steeper than the observation. So the CCN can be more effectively converted to droplet number in the model than in the observation. And the second feature I noticed is that in the observation, you see the samples are much more scattered. And in the model, it's more on along this line. So it's much tighter connection between aerosol and CCN and the droplet number. So I think there are 2 issues here in our model. And I attribute that to overly effective aerosol activation problem. And the second issue here is this very difficult problem. That's the leak-water path ND joint histogram. So this is to describe how cloud water changes when you have increasing droplet number. So we know that for the famous aerosols lifetime effect is that if you have more aerosols and more droplets, that you will decrease the precipitation efficiency, and the clouds tend not to precipitate. So the clouds will be thicker, and that's why you should expect when you increase droplet number, leak-water path should increase. But that's not what the real world is telling us. So this is the famous inverted V shape, first identified by Ed Greispierre in UK, Imperial College London. And then a lot of people do all kinds of studies in the observations in LES and so on and so forth. I believe Marcus showed a figure from the LES results also show this inverted V behavior. So the people then start to understand the behavior. So they develop theories to say that, well, in this regime, when you're in a clean condition, you increase the droplet number, then leak-water path will increase. So this is the precipitation suppression. But once you have way more droplet numbers, so the precipitation suppression effects is saturated, and then the other processes like the sedimentation entrainment feedback loop, or the decoupled boundary layer dynamics, and these 2 mechanisms proposed by Eckermann et al. And Bretherton et al. From, I think, more than 15 years ago now, or 20 years ago now, are still the dominant theory to explain this behavior. And I don't need to convince you that the model and the observation show very different results. So here we're seeing not inverted V, but a V shape. And I would say because the ND PDF look like this, so it actually shows the model basically has the precipitation suppression. We don't understand what this is, but there are much less samples in this region. Yeah?
So in the previous slide, you said that the ACI was like within the range of observations from like a TOA perspective. And then you're saying that, but it's too sensitive for the surface temperature. Is that
The model is very sensitive to aerosol perturbations in our model. And so this has been a scientific debate between me and a few others. I find evidence from other models. For example, CSM's aerosol effective radiative forcing is basically the same as E3SM, but they don't have that surface temperature issue as that we have. And then the other example is that I was handling a paper in GMD that's about the UK Met Office Earth System model version 1 and version 1.1. They compare these two models. And the two models have basically the same aerosol effective radiative forcing, and one of them have a very strong cooling like we have, and the other one doesn't have that. So I would say that the forcing is one thing, and the system's response is a different thing.
and what time scale is that response? Like, it looked quite fast on the like the plot.
So the time scale, where am I? Yes. So of course, since you asked that, I bet that you are thinking about the heat capacity of the ocean and heat uptake in the ocean and land. I think they are playing a role. Yeah. So we want to see if we can really address those parameterization deficiency using the new artificial intelligence framework. So our original plan was to collect a lot of data from ARM, from satellites, and from other sources, and then we have this particle resolved aerosol model, and then coupled with the large eddy simulations. So we have a lot of those data, and so this is a paper that we finally got published. It's archived about 160 terabytes of LES simulations with different aerosols and coupled with the beam microphysics, so we can really track the droplet and collision coalesce process and size distribution evolution, as well as in different aerosol and cloud regime conditions. And then we know there's a lot of aerosol processes. We can build emulators because some of those processes are super expensive, and we can just hopefully use neural network to speed up the calculation. And then we put them in an E3SM framework and develop software to do the interface. So that's being introduced by several people already. Yeah. And in general, I think not just our group, but many other groups in the community already found that the AI models are doing a good job emulating their training data. And once they are trained, the AI models are much cheaper than physical models generally, but there are exceptions, of course. It depends on the system you are trying to emulate. So when we were at that point, so this is basically when I wrote the title and abstract several months ago for this workshop, I thought that this is the idea to talk about. But then things changed in the last several months because we started to question ourselves. Is this approach really advancing the science? Do we really, if we're only emulating the data and the emulator is not going to produce anything we didn't know. And so that's not satisfactory for us as a scientist. So questions that we start to ponder is that, after we increase the resolution, so as many of you might know, that E3SM is going to completely C++ COCO's framework and can run very fast on the GPU machines. And we have the aerosol module supported in the C++ COCO's framework and still has some performance issues, but yeah, it runs, it can do a lot of GPU, calculate on a lot of GPU nodes and runs fast. But then we wonder, can this data-driven or hybrid Earth system model outperform the training data? And can they achieve desirable predictability for the right reason? And how do we couple data-driven parameterizations? What about adjustments and feedback that are not explicitly represented? So about this adjustment process, I was referring to this entrainment feedback loop that reduces the liquid path when you increase droplet number. There's no parameterization in the model to represent this process. So it depends on the model to figure out itself. So it's an emergent behavior of the system. It's not part of the process representation. And how do you account for those? So I decided to change my title to this. I think human intelligence is still important in this whole complex. Okay, so our science object, our science objective is to accurately predict the aerosol current interactions and their radiative effects at this point. And we tackle, because we're focusing on their radiative effects, so you know that there's direct and indirect effects. So the direct effects are aerosol scatter and absorb solar and terrestrial radiation. So we want to take a look at the aerosol optics. Of course, aerosol optics is a results of aerosol mixing ratios and numbers and size distribution and all other things all together. And the indirect effect has two parts. One is the activation. Aerosol activates and form cloud droplets. And then you can suppress precipitation. So this is a warming process. So it's very apparent that we start looking at these three processes and see if we can use the current AI machine learning to help us to better represent these processes. But we can't just say, well, my parameterization is better than anybody else. We need to have a ground truth or the observations to back us up. So we need to have those process-oriented metrics. So I'm going to mostly talk about these four different topics that we use machine learning to help us improve the science. So first is the aerosol optics, and we built a aerosol optics emulator, and this is based on the Me code, the Me calculation. So we first generate a high-resolution lookup table from the Me calculation, covering a wide range of aerosol conditions, size, and compositions, and so on and so forth. And then use a neural network to emulate that. So we first try a random, because it's more expensive than we expected. So we first tried this random neural network. So we randomly dropped neurons that didn't really contribute to root mean square error reduction. So that reduces the number of parameters, and so the neural network is much cheaper. But then in the end, we decided not to use that because it doesn't seem to have a lot of benefit and it becomes harder to interpret the results. And then we still use this fully coupled feed-forward neural network. And then on top of the traditional internal mixing assumption, we also try this shared core optics. That's when you don't assume that all kinds of aerosol particles are well mixed as one property. You assume that the black carbon is in the middle, and then it can be coated by sulfate aerosols. So there's this lensing effect that can enhance the aerosol absorption. So we account for that and build another emulator. And this is the results comparing the parameterization and the truth. So the original scheme that's used in many Earth system models is based on Steve Gann's early work. Actually shows this behavior. This is the shortwave extinction. So you can see that when shortwave aerosol extinction is high, the parameterization is actually unstable. So this parameterization is built on a lower resolution Me code lookup table, and then use Chebyshev polynomials to do the fitting. And we built a deep neural network, and the results are bounded by these two red lines. So it's much better than the original parameterization. And this is not truth. This is a representation of truth, because Me calculation still assumes aerosol particles are spherical, and we know they are not spherical. And so they can look like this, and we don't know how to treat that. So, but then there are laboratory experiments that try to, account for these different shapes, different weird morphology, and then to assess its radiative effects. And we build a different neural network to correct the shared core optics absorption. And then that's published in this paper last year in One Earth. And that will reduce the aerosol absorption compared to shear core, but will have larger aerosol absorption compared to internal mixing, so it's in the middle. And the surprising result is that, well, we changed the aerosol optics, but it actually changed the aerosol cloud interaction effective radiative forcing a lot, like half a watt. So this is an unexpected result. And after we analyzed the results, we found that it's because the semi-direct effect becomes very important. It becomes dominant, actually. And semi-direct effect says that when aerosols in the air is absorbing this radiation and heat the lower atmosphere, especially near the boundary layer top, it can evaporate the clouds. And so when it does that, this aerosol-induced cloud brightness effect is being offset and is weakened. So here, I found it interesting because when traditional wisdom is telling us that this reduction in liquid path when you increase droplet number is due to entrainment sedimentation feedback loop. In GCM, we found that there's a possibility that a second or alternative pathway is possible, that is through the semi-direct effect. And the reason why no other Earth system model have ever found this is because they don't have the shear core optics, I think. So that the semi-direct effect has never been very obvious in the Earth system models before. And the second thing I want to mention is this aerosol activation emulator. So we have actually done quite a lot of work since many years ago, since 2020. Sam Silva, a postdoc at PNL at the time, and now an assistant professor at the USC. He did this work by using the cloud parcel model to generate a lot of training data for the 4-mole version of the modal aerosol module, or MEM4. And this is the original Abdul-Razik and Gan activation schemes, and compare with the parcel model truth, you can see that it's not doing a good job. And the neural network, of course, is much better. And then we put that in the model that increased the droplet number significantly. This is comparing the new DNN model with the original default E3SM model. So remember when we started this conversation, I think I mentioned that the number one, the first obvious bias for most Earth system models is that we have a low droplet number bias. And this activation scheme seems to be able to fix that problem. But we didn't really pursue much longer along this line at that time, because I noticed something that's not satisfactory, which is that I found that, in MEM4, we have 4 modes. That's Aiken mode, accumulation mode, coarse mode, and primary carbon mode. And in this implementation, I found that for when you have this, no matter if you have the deep neural network or the original Abdul-Razik and Gan scheme, the activation fraction for the accumulation mode aerosol is almost near 100% all the time. So this is strange. And for the Aiken mode aerosol, it's not high enough. So this creates problems, right? Because in the past, I think 10 years, people have been noticing that the models tend to produce very strong aerosol effects, but the real world, it doesn't, right? And the hypothesis is that maybe in the real world, Aiken mode aerosol acts as a buffering mechanism, because you have a lot of Aiken mode aerosols, but because they are so small, so they don't, traditionally we thought that they don't typically activate. But if now you allow those smaller particles to activate and form droplets, then you solve 2 problems. Then low droplet number bias will be solved, and you have an abundance of the background Aiken mode aerosols that's available. And so, but the deep neural network doesn't seem to be able to capture that, and Abdul-Razik Gan scheme doesn't catch that. And we did a very...
How come your solution does a better job at the tropics rather than the mid-latitude? here.
Do a better job in the tropics.
Yeah, it looks like the differences are near zero in this region, and they.
No, it just means there's not a lot of clouds here. So this is the deep neural network minus the E3SM default. So red means that the new model produced more droplet number.
Oh, better. Okay.
Yeah. And we try to analyze if the kinetic limitations are accounted for. That means when you have multiple modes of aerosol, have a lot of achemol aerosols, that they should compete for water vapor with the accumulation mode aerosol. So if you increase achemol aerosol, the accumulation mode aerosol activation fraction should decrease. And it has a little bit of that, but not very strong. And this is Sang-Dak Yu working with us and Mike Preacher at the time to develop a two-step process workflow to do this hyperparameter tuning, optimization, and selection in a very efficient way. And we tried a lot of methods and just didn't really solve the problems. Until very recently, Andrew guys pick up this problem again. And now this time we found that there are two issues. One is that the neural network, the very simple deep neural network might not be able to do the job well enough. And so he implemented this attention mechanisms in there, and that will be able to capture information in other modes and other informations that's resides in other places. And that makes a much better prediction, but that's not the most critical thing. The most critical thing is that he found that the partial model that we use and everybody use, and is in the 2011 GAN paper also, uses a approximation for calculating the supersaturation, maximum supersaturation. And he tracked down that equation and found that it's from a 1950 textbook, and that approximation works only when the air parcel is near saturation. And when you are in an Earth system grid box and your relative humidity is 90%, 85%, that approximation actually doesn't work. So he fixed that, and he implemented a correct calculation for the supersaturation. And now the accumulation mode aerosol doesn't always activate. And then when you have a stronger updrafts, you allow achemol aerosol to activate. So we kind of have the physics right now. So we now have the right training data matched with a right neural network architecture, so we can have a better parameterization. So I think this is a great example why we need both human and artificial intelligence. You can't just grab the model, run and produce data, and then run your training algorithms. Okay, and on top of that, after activation parameterization is done, we still need to couple it with the model. And the current way of coupling the model is that we take the grid box, 100 kilometer grid box, TKE, and then calculate the square root of that and times a scale factor, and use that to be the updraft, the proxy for updraft velocity. And that's clearly not the right approach. And in our model, we use this double Gaussian distribution for the updraft velocity. So we rewrite the formulation so that we diagnose the updraft part of the cloudy part of the cell. That's the only part of the grid that will go through the activation. So you can imagine that if we calculate only the updraft velocity from that portion, that updraft velocity is going to be much larger than if you do a grid box mean that includes both the clear sky and the downdraft, right? So this is how you will have the stronger updraft that can activate achemol aerosol. And also, this is another important thing that for a 1 degree model, when it couples with the land model, the land model, like what Tapio said on Tuesday, we as atmospheric scientists, we think the land model will provide us the land surface flux. And in the current parameterization, because even though the atmosphere model has the subgrid representation for those turbulence and structures and turbulent mixing structure, and the land has those subgrid variability parameterization as well. But when the two-component model communicate, they communicate in grid box mean sense. So all the information done in different components are lost in the communication. And we tried the traditional approach by modifying this theory and how that they can carry those information across the component model and run the simulation. Didn't really make much difference in the atmospheric simulations. So then finally we decided that's also when the E3SM's first 3-kilometer configurations become available. So we thought that maybe we should just run a 3-kilometer E3SM model simulations and archive all this informations. And then we calculate the subgrid variability of temperature and humidity from that 3-kilometer resolution run, and then calculate those variability and covariance and with respect to a 1-degree grid box for the entire land surface, and then feed that information as the lower boundary condition for our turbulence scheme. And so we did that, and that doesn't directly affect your turbulent flux of latent heat flux or sensible heat flux. They are the same. But because you change the variance and covariance of temperature and humidity at the surface, it will change your turbulent mixing of temperature and humidity, and it will also change the skewness of your PDF. And that will change this parameterization, and that will change the activation and cloud properties and structures. So these things are another example why the domain expertise and the artificial intelligence, when they combine together, we can do great things. And when we put them together, well, it again reduces the aerosol effective radiative forcing by about 0.2 watts. That's just the activation scheme. But when we couple with those things that I mentioned before, that's another 0.3 watts per square meter reduction, right? Okay. So you might want to ask that, well, do we really need to fix activation first and then fix the updraft and turbulent mixing, and then, or we can just do nothing and let the compensating error do its trick, and let 2 or 3 runs to make it right. So I don't think it's a good idea, because you can analyze this is again from this great PhD student Li Tai Kang's work. She did this analyzing the aerosol number larger than 70 nanometers in the precipitating conditions and non-precipitating conditions. You can see clearly there are 2 modes. So when you precipitate, you have this wet scavenging, so you have much lower aerosol number concentration. But in E3SM, the 2 modes are kind of overlapped together. So that means we don't have a good enough wet scavenging, and we don't have enough activation, and all these processes are not done correctly. So even if you seem like maybe you can use several runs to make it right, but if they are not correct in the process level, the physics is not right, how can we expect it make the right simulations and predictions that resemble the real world? So my own philosophy is that we believe Earth is a complex system, and Earth system models need to be complex enough to permit those adjustment, feedback, and buffering behaviors that resemble the real world. That's my philosophy. Okay, so this is something that Marcus mentioned, that we have been working with Hugh Morrison on this, and after many days, weeks, and months coding this up, we're finally very close to finish. So the idea, like what Marcus said on Tuesday, from observations and from theory, we know that there are the cloud droplets can collide and then form bigger droplets. And when they're big enough, we call that, and then overcome the buoyancy, and then becomes too heavy, and then drop out of the clouds, and we call that rain or precipitation. And so you know that in terms of the physical process, it's just the collision covalence process. But then because we try to fit that into a two-category bulk microphysics scheme, so we invent we decompose that into 4 different unphysical processes. That's autoconversion or rain initiation, accretion or rain growth, cloud droplet self-collection, and rain droplet collection or breakup. And because of that, and we invent tunable parameters to control its behavior, and they are totally non-physical. And so Hugh wants to make it right, and so what we did is that we no longer separate cloud and rain categories. So in terms of, instead of a 2-category warm liquid microphysics, we do 1 category. But we need to acknowledge that they are, in observations, there are usually clearly 2 distinct modes. And we can't just use one gamma distribution to represent that. So we introduce a double gamma distribution. And then, so to better represent that double gamma distribution, we need to use 4 moments. So now instead of 2 category, 2 moments, and that has the mass and number for rain and clouds, 4 prognostic variables. Now we have 1 category that's liquid and 4 moments. So we keep the number of prognostic variables the same. And then in the model, when it goes to the collision covalence process, then we use a beam model to solve that. So we first map the moments to beam to beam representation, and do the collision covalence kernel calculation, and then remap that back to the moments, and then back it out. So this calculation, because this mapping is not, there's no analytical solution, and so we need to use a iterative numerical solver to do that, and it's very slow. So then we first try to use a neural network to replace the iterative solver, and that gives us 2,400 times speed up in that calculation. So this makes that implementation in an Earth system model possible. And then we further took another approach, that is to bypass the entire beam kernel collision covalence solver, just directly use a neural network to predict the moment tendencies. And then after this is done, we still need to go couple with the Earth system model, which only knows what QC, QR, NC, NR are. And so we need to do this mapping. And it gives us some differences in terms of aerosol forcing. It's 0.1 watts per square meter. And then what we have been working on is that do a much larger surgery to the code, which is that we no longer allow 2 categories in the rest of the model. We now just map them to a Q1, Q2, N1, N2, so 2 modes, mass and number. And both Q1, Q2 can be cloud, or they can both be rain, and they can be one of each. And so this is how we do it. And so I remember on Tuesday, somebody asked that, or can you just evac the moments and use moments, this M0346 as the prognostic variables in the entire model. And yes, we can. And Hugh actually tried that in LES, and it doesn't produce good results. And like what Marcus said, it has numerical broadening issues for the size distribution. So actually a better solution is to map these 4 moments to Q1, Q2, N1, N2, but don't assume one of them is cloud or rain. And that's, so far, it gives us the best solution. So, I mean, we have completed the code implementation, and model compiles and runs. It produces results that's the droplet number is 6,000 times larger, which can't be right. And I couldn't figure out what's wrong as last week, so I can't update you the results today. Yeah.
When you're passing around that state, like the Q1, Q2, N1, N2, And they're both in one category, or is it just like two modes in one category?
Yeah.
Okay, thanks.
And another thing I didn't mention, but since you said this, actually the rest of the model still needs to know if you are raining or not. Like a wet scavenging of aerosol, you need to know if it's rain. So what we do is that we implement a small code that to see if this mode is cloud or rain size. That if it's rain, then it will help remove the aerosols. If not, then no. And things like radiation also, yeah. And then this is a study that we want to address the low droplet number or low background aerosol problem, and we improve the DMS emissions and the chemistry, and found that as you go to more and more complex and correct the implementation of the DMS chemistry and the emissions, the model starts to bridge the gap and reach a better agreement with the observations. And my current postdoc is working on this, building a neural network to emulate this DMS concentrations in the surface based purely on observations. There's no model results. And the model is producing a very good results. The R value is 0.95 in this particular one for the linear scale. And for the log 10 scale, it's 0.92. So they are both very good. And the climatology that she produced is like this. It's very reasonable. It's consistent with the latest NOAA estimates. But the good thing about this is that it's just not just the climatology, can be coupled with the model to do this interactively. And this piece is about the observational analysis framework. So this is an inverted V shape. And Matt Christensen lead this work to find that this behavior only appears in a 1 degree data, satellite data. But if you process the data from the level 2 track data and put them on 5 kilometer grid, 10 kilometer grid, and all different kind of resolution, you will start to find that it's not an inverted V shape anymore. When you go to high resolution, it's more like an M shape. And then why is there an M shape, right? If it's an M shape, we can use simple precipitation suppression and then entrainment to explain this behavior. So he then built a random forest model with a lot of cloud controlling factors and also the droplet number to predict the liquid water path. And the random forest model appears to be a very good model. But then when then we spent 8 months stuck here because the model, when you try to use the model to predict the liquid water path given the wide range of ND while fixing other things, it always produced this inverted V shape. There's no M shape, and we didn't understand why, so this where we got stuck. But I told him to give up, let's just move on, and he didn't want to give up. And it pays off. He finally found that when you use the same random forest model, and then change the ND, but don't keep all other controlling factors fixed, you allow them to vary when you vary the droplet number. And now you started to see the M shape. So I think this is a great, huge implications here. That means the liquid water path ND relationship that we see in the observations is a result of two things. One is the causality, the real interactions between droplet number, the aerosols, and the cloud liquid water. And the other is the co-variability between aerosol and all these other meteorological factors and cloud controlling factors. So how do you tease out the true causality from a very complex system that everything co-varies, right? So this is the place where I think the only reason we found this is because the random forest model is good enough to identify this, and we were able to show this. And so then finally we're going to put everything together and then to see what the effects are on the aerosol radiative effects. And this is a paper we published 2 years ago, and that builds in 11 new chemical reactions for the new particle formation. So we have more 8 more aerosol, and these are a lot of experiments we did. And blue ones that are the ones that I mentioned to you before. And I want to point out that, so this is what I mentioned before, that all these features reduces the aerosol effective radiative forcing. But then the one that stands out that's really interesting and unexpected is that you improve the aerosol optics that should change only the aerosol direct radiative effects, but it actually changes the indirect effects. And the part that's really exciting is that it changes the adjustments term. So no other features in clouds and precipitation processes and turbulence that we implemented to change the adjustments, which we were traditionally thought as a cloud process. So the semi-direct effect, I think, only really produce an alternative pathway to get the adjustment term right. And want to mention this. So many people, I think Tapio also mentioned this on Tuesday, that we want to trust the AI model, we want to impose physical constraints and physical laws. But in emulating aerosol chemistry or aerosol microphysics, this is not very easy to do. So for example, on the left is the relationship between the DMS and the sea surface temperature out of that DMS emulator I mentioned. So this is purely observational driven, and this relationship doesn't really make sense. We don't understand it. And currently, and that we try very hard to do a literature review for the past 20 years, and there's no very clear guidance on how the ocean BGC really works, because there is also a very complex problems. So this is the issue, that when we don't really understand the physics, how do we impose the physics constraint? And the second issue is that, well, maybe we can just impose a very fundamental physics laws like conservation. Well, in here, you can see that because the Earth system model don't have the ability to represent all possible chemical reactions in the atmosphere, there are probably millions of reactions. In E3SM, we represent 3 reactions or 4 reactions for sulfate. And so for this DMS, you can see that we don't really conserve sulfur mass in this equation, because there are other processes that will take care of that. So in this representation, we don't have mass conservation. So how do you impose a mass conservation law in the AI model? So these are the things that we need to consider when we try to use physics laws to inform or to constrain a machine learning model. So in the end, I want to say that I think still in this era, AI becomes very useful for us, but then human intelligence are still needed, and there are many examples. And building this fast and accurate process surrogates, I think is now doable, and it's a very straightforward procedure to do. Earth system model simulations can still be limited by fundamental and structural assumptions carried in the host model. So like the particle shape, subgrid distribution, size distribution, and things like that. And improving those couplings sometimes change the results more significant than changing the process representation itself. And they can have unexpected improvements someplace else as well. Observationally derived AI models disentangles the complex intertwining co-variability and causality. I think this is a really exciting area where we can really learn from the AI model to identify new physics that we didn't know before. So I think I'm going to skip the next steps here. Okay. Thank you.